And hello, welcome YouTube. Welcome to this video. So as you can see, I'm actually doing some frequency response now on the system that we have just made. The baseline heater power is at 15 dimensionless units. Of course, I'll upload all of this to Git. Okay, and do make sure if you want to use this write to measurement file, change the file path in case you git clone it to your local directory. Okay, if you git clone it to your local directory, make sure you have the correct file path to your desktop. I'm not going to edit it for you, but yeah, that's what we have. Okay, so we have a frequency response. My baseline heater power fraction is around 15. My heater oscillation amplitude is around 2. All arbitrary units, of course, and you'll be able to find stuff on my labview YouTube. Okay, you should find it on my labview YouTube thing, and you should be able to find this Git link in the description. Alright, no problem. Okay, so now what we can do is basically just do frequency response, and basically from 100 seconds onwards, you can see that both of these oscillations are at a very constant frequency. Okay, and they oscillate in a very small amplitudes relative to each other. So we can test it for several frequencies, and I'm going to stop now. Okay, so this maybe you can consider a first data set at 0.5 hertz. Okay, so let's make a folder here. Okay, and my test data. Okay, and let's put copy and paste this here. Okay, 0.5 hertz and 0.5 hertz, and we can deal with it later. Okay, we should be able to git clone and git push and everything. So now I don't want it to be 0.5 hertz. I want it to be maybe 1 hertz. Okay, let's try 1 hertz, and then we'll just press run. You can see that the thing takes some time to stabilize. So give or take maybe around yeah, we'll start to see when these sine waves actually pop up. So it's this signal is sort of stabilizing and all that. And you can take a look at the time. The time is around 25 seconds ish. You can see the sine waves becoming more and more obvious. Okay, so okay, you can see give or take about a minute in. I think it should stabilize roughly about 1 minute in. Okay, 1 minute in will be your stabilizing time, so to speak. Yeah, so we can just let this run for about a minute or so. And this is how frequency response is done. You take a look at the input, you take a look at the output, and you just run it over. Well, as long as this thing sort of stabilizes into a sine wave of sorts, you should be able to use that data. So yeah, for very high frequencies, for example, relatively high frequencies for this system is about 1 hertz, which is more than on any of the poles we might get. Yeah, more than any of the typical process times. Yeah, I can see that this thing actually takes very fast to stabilizes pretty quickly, and we'll just stop at about 120 seconds, cause that's about, give or take, yeah, give or take maybe 10 oscillations. I don't know. It's about a minute worth of oscillations. Okay, so there are lots of oscillations here. So I just stop, and we can use a MATLAB script to, of course, get it done. So I'm going to rename these two as 1 hertz. Okay, okay. Maybe I'll put underscore or yeah, 1 hertz. Okay. And the output file will also be 1 hertz. And there you go. Of course, you can do this a little bit more in an automated way. You can actually define the way your file, you can define the name your file is going to be by checking what is the frequency of your oscillator and everything. But I'm not going to do that here. I'm just going to do that a bit more manually this time. So yeah, what I'm saying is that if you take the oscillation frequency, you can use that as your input to your file name, okay, and you can append that to your file name, no problem. But that's not what I'm going to do for the time being. Okay, so I'm not going to go into higher frequency ranges now, because you can see the oscillations are so small, they are barely noticeable. So it's about 239.3, then it's 239.1. So I'm not going to do any sort of that kind of thing like that. I'm not going to bother. Okay, so let's change the heater oscillation to maybe 0.01 hertz. So now we'll need to take a lot longer. Okay, so okay, that should take about a minute or so. And you can see these oscillations take a very long time. 0.01 hertz means one oscillation every give or take every 100 seconds, I think. Every 100 seconds you'll have one full oscillation. That's how slow this thing is. So we might need to wait about 10 oscillations for this thing to finish. Okay, so that's any time from could be 20 minutes, all this it may take about 20 minutes just to get this test done. Okay, and you can imagine for very low frequencies, for example 0.001 hertz, 1 times 10 to the minus 3, such what do you call it? Such tests may take on the order of a few hours just to finish. Okay, so the thing with frequency response testing for very low periods, low frequencies, sorry, very high periods and low frequencies, you can see that these tests actually begin to become very, very time consuming. Okay, so and at least for us, if the system can be considered linear within a very short within the interval of that we are testing, if we assume that the system is linear, we can actually do this. We can actually, instead of using a clean sine wave as the input, we can use multiple superimposed sine waves as the input. Okay, or better yet, you can use some special sequences such as sawtooth or this square wave. Square wave sequences, actually they superimpose a lot of sine waves, and that's one way of doing it. And even better, you can use periodic pseudo random sequence. Okay, so this is a motivation for us to actually use some of these different methods to test frequencies over a long range, so that let's say if you have a 10,000 second test, you can actually test multiple frequencies at one go. That is of course assuming that linearity holds, and for this situation it looks like it does. Okay, it looks like it does. So of course I'm going to let this thing run for a while, maybe let it run to about 1000 seconds, and let's see what happens. Yeah, I can see frequency response testing in a real system. If you are talking about real reactors, step response is easy, but if you have chemical reactor or what, that's you need to test at very low frequencies to do the control system. Then of course you might want to use step response, or some other kind of inputs so that you can test these things quickly at multiple frequencies. Okay, so yeah, at least it goes to show, you know, our system's running nicely, but we might want to use some other methods and inputs. Okay, so that's going to be a topic of the next video. Okay, at least now it shows that yeah, we might need some other special sequences instead of just clean sine waves as our input. Okay, and that's the whole point I'm trying to say in this video, why we want to use special sequences in our frequency response testing. Okay, not just sine waves, but other things as well for low frequencies. Okay. So thanks for watching. I'll see you guys again. Bye bye.